The practical implementation of hydraulic DMUs after the war marked the beginning of the acceleration of non-electrified JNR lines, evolving into semi-expresses, expresses, and limited expresses, resulting in reduced travel times in various regions. This increased mobility of people and facilitated economic activities, contributing to regional development. However, from the late 1950s, economic growth and technological advancements ushered in a new era of competition, and the development of automobiles and road networks began to seriously impact JNR's management. Even though travelers were freed from journeys shrouded in steam locomotive smoke, and significant speed improvements were achieved, people who tasted the convenience of private cars gradually moved away from railways. Unlike major metropolitan areas that were already suffering from severe traffic congestion, rural areas had mostly empty roads with few signals. Despite the common presence of unpaved and rough roads at the time, automobile transportation continued to increase. As modern travel by EMUs and DMUs became commonplace, the next step was needed to curb the shift away from railways. JNR's top priority was speed improvement. This led to the realization of the groundbreaking Shinkansen, which can be considered the world's first full-scale high-speed railway. To spread its effects to conventional lines, a nationwide speed increase was planned. EMUs already had surplus output, and by increasing the ratio of motorized cars, it became commonplace to run at the maximum speed allowed by the track. The next challenge was to achieve high speeds on curves, essentially overcoming the limitations imposed by the tracks. On the other hand, DMUs had only about half the practical performance of EMUs, significantly lagging in acceleration performance and gradient balancing speed. As a solution, new series DMUs such as the Kiha 90 and 91 were introduced. By providing approximately 1.5 times the output of conventional DMUs, they achieved generally sufficient performance on regional lines with successive sharp curves. In the 1960s, JNR's financial situation rapidly deteriorated. Amid the accelerating spread of automobiles and road development, the dream of a nationwide Shinkansen network with enormous construction costs became unrealistic, leading JNR to further pursue the speed improvement of conventional lines. The development of new types of vehicles began, capable of high-speed curve passage through low center of gravity and weight reduction, with the body tilt mechanism suppressing excess centrifugal force on passengers. For EMUs, as mentioned earlier, there was already surplus capacity, and many electrified routes had solid track structures, allowing for the development of high-speed vehicles as an extension of existing technology. However, for DMUs, it wasn't so simple. Even with new series DMUs, the balancing speed on a 25 per mil uphill gradient was around 60 km per hour to 69 km per hour, depending on the formation. The speed limit on a curve with a 300-meter radius for general vehicles was 60 km per hour. For high-performance limited express EMUs and DMUs, it was 65 km per hour, 5 km higher. At that time, JNR aimed to achieve a passing speed of 80 km per hour on these curves, 20 km higher than general vehicles. For EMUs, even with conventional vehicles, it was possible to climb at this speed with a formation of a 2:1 mountain time ratio. However, it was much more challenging for DMUs. As mentioned in the video, what if the 181 series had a two-stage transmission? Even with a two-stage transmission, it doesn't reach 80 km per hour. The JR Shikoku 2000 series can reach over 90 km per hour, but even comparing practical performance, the 2000 series is 70 horsepower more powerful. In addition, with thorough weight reduction, this speed was somehow achieved. At that time, such multi-stage transmissions had not yet been realized, and the remaining option was to improve engine output. Later, the improved high-speed version of the 183 series, which would be deployed in Hokkaido, adopted intercoolers and direct injection, eventually achieving an output of 660 horsepower with the DML30 series. Let's assume that during the JNR era, the 181 series could hypothetically have been upgraded to 660 horsepower. With the maximum usable output of the 181 series, this represents a 70 horsepower increase, Yet it still does not reach 80 km per hour on a 25 per mile gradient. Even for the lightweight 2000 series, if it lacks a two-stage transmission mechanism, it cannot reach 80 km per hour under using air conditioning. What happens if the output is further increased? Raising the maximum usable output to 730 horsepower allows it to climb a 25 per mile gradient at 80 km per hour. However, this assumes there is no weight increase due to the output enhancement. If the engine and transmission together become 2 tons heavier, the calculation shows that 750 horsepower or more is needed to achieve 80 km per hour. Naturally, it was impossible to create such a powerful engine with the DMU engine technology of the time. Even if such an engine could have been made back then, the loaded weight would be 50 tons, making it heavier than AC-DC dual system EMUs. To pass curves at high speed with this weight, track reinforcement on par with major electrified mainlines would be required. In the end, with the diesel technology of the time, having vehicles capable of high-speed operation without reducing speed on sections with sharp curves and steep gradients was a pipe dream. Around the same time, overseas in the realm of high-speed rail, they were struggling with the limitations of diesel technology. Inspired by the success of Japan's Shinkansen, high-speed rail development became active in Europe and America. However, these countries had not yet established economically viable and practical current collection technologies, and they couldn't immediately mimic the Shinkansen to run high-speed electric trains. Diesels, which didn't require current collection equipment, were considered to have a practical limit of around 200 km per hour due to weight, and surpassing the Shinkansen was unattainable. Hence, Europe and America swiftly adopted gas turbines. Inspired by this, Japan also began developing and testing gas turbine vehicles to overcome the limitations of diesel. The year after the new Series 181 started commercial operation as the Limited Express Shinano, in 1969, they began testing modified Kiha 07 vehicles, which I have introduced in other videos. They were making progress towards the practical implementation of lightweight, high-output vehicles capable of high-speed operation on the fragile tracks of non-electrified regional lines. At that time, various forms of gas turbine vehicles were considered, from those equipped with gas turbines in regular vehicles to those with articulated structures advantageous for a low center of gravity. Among these, a power-concentrated vehicle was proposed, which was rare for Japan at the time. Diesel vehicles had heavy power units, and if concentrated, the vehicle would become extremely heavy, making high-speed operation difficult on the fragile tracks of regional submain lines. However, with gas turbines, the situation changes entirely. Especially with mechanical power transmission, it can be lighter than both diesel and electric vehicles of the time, making the concentrated power format a viable option even in Japan. At that time, for a DMU with a conventional 20-meter body, it was considered that installing a 600 horsepower engine was the limit to keep the axle load within 11 tons. However, with gas turbines, the situation changes dramatically. It was considered possible to increase the output by about 3 to 5 times, effectively giving locomotive class output. At the time, domestically produced gas turbines available for vehicle use included 2 types, the CT58 series and the T53 series, which were introduced in another video. These were licensed and produced domestically by Ishikawa Harima and Kawasaki Heavy Industries, respectively, and were maintained locally. Both were used in helicopters and had outputs ranging from 1,000 to 1,400 horsepower. They envisioned installing 2 of these engines on vehicles at both ends of the formation, and to ensure performance of 80 km per hour on the aforementioned 25 per mile gradient, the formation included 6 middle bogie cars. The gas turbines themselves were very compact, and even with 2 units, they could easily fit under the floor. However, gas turbines had significantly higher intake and exhaust flow rates than diesel engines, requiring larger ducts to handle them. Consequently, the size of the mufflers also became larger, preventing all components from fitting under the floor. Thus, these components were designed to be placed collectively in the part equivalent to the machinery room of the 181 series. The engines alone weighed only about 300 kilograms combined, so placing them above the floor had little adverse effect on lowering the center of gravity. Lowering the floor of the vehicle was considered far more effective for reducing the center of gravity. Unlike diesels, which transmitted a dull low-frequency noise and vibration to the passenger compartment, gas turbines produced almost no vibration, and their noise was mainly high frequency, which could be significantly mitigated by simple shielding. Therefore, it was not a major concern to place passenger compartments adjacent to the machinery room. However, since the intake and exhaust ports opened directly to the outside, external noise became a problem. Automobile gas turbines equipped with heat exchangers for fuel efficiency had greatly reduced external noise, but helicopter gas turbines without these required high performance, large mufflers to avoid noise issues. The machinery room of the 181 series had ample space as it housed the radiator for cooling the 750 horsepower engine. However, addressing the gas turbine's weakness of ineffective engine braking was necessary. At that time, with the development of synthetic brake shoes, lightweight high-speed vehicles could handle the speeds of conventional lines with friction brakes, except on very long downhill gradients. However, frequent brake use had to be considered for high-speed operation on lines with strict turnout limits and many sharp curves, leading to plans to equip dynamic brakes. Since there was no hydraulic transmission, converter brakes could not be used, and they planned to equip a retarder similar to the one being developed for the DE50, using a fluid coupling. Gas turbines themselves required little cooling, and without the heat-generating hydraulic transmission, mechanical gas turbine vehicles lacked cooling equipment like radiators. With diesel drive, engine, and transmission cooling systems could be repurposed for brake cooling, but this was not possible with gas turbines. During the peak of automobile gas turbine research, there were attempts to directly connect the power turbine and compressor to achieve powerful engine braking, but such a direct connection was unfeasible for large output railway applications. Ultimately, a dedicated radiator was added to dissipate the brake energy absorbed by the fluid coupling as heat. This was to be installed at the rear of the machinery room, near the passenger compartment, with forced cooling fans on the roof to exhaust the heat. To secure this space, the machinery room was made wider than that of the 181 series, resulting in a seating capacity reduced by 4 passengers. The power shafts of the 2 engines and fluid couplings were connected and guided under the floor. This structure drove not only the front bogie, but also the rear bogie via long propulsion shafts, achieving 4 driven axles, or all-axle drive. Due to the absence of a transmission, the starting tractive effort was weak, meaning wheel slip was not a significant concern. However, in later tests with the Kiha 391, despite having 1,000 horsepower and 2-axle drive, wheel slip frequently occurred in the middle speed range, potentially indicating challenges for lightweight vehicles using a power-concentrated format. Additionally, at the time, there were no concepts for propulsion shafts with integrated bearings as developed for the 2000 series, leaving the challenge of adapting to tilting car bodies unresolved. Among the middle bogie cars, 2 had power engines mounted under the floor. At that time, with the spread of air conditioning in DMU express trains, noise from the power engines became an issue, and there was consideration of using aircraft power units to address this. While these had the advantage of being lightweight and low noise, small gas turbine generators were fuel inefficient. Therefore, for systems heavily dependent on generators for heating and cooling, like limited expresses, year-round use was the principle, leading to unfavorable fuel consumption. As a result, they opted to install the same power sets as the 181 series. In a 2M6T formation, the loaded weight was estimated to be 310 tons, enabling over 70 tons of weight reduction compared to an equivalent 181 series formation. Using the same engine output setting and reduction ratio as the Kiha 391, the tractive effort was as follows: The starting tractive effort was just over 14 tons, which seemed weak for an output of 4,200 horsepower. With only 8 driving axles per formation, wheel slip was a concern, but assuming an adhesion coefficient of 0.2, the adhesion limit was 17.6 tons, suggesting that starting would be manageable. Let's overlay this with the corresponding 181 Series 7M1T formation. Predictably, the 181 series with its transmission exhibited greater tractive effort at low speeds. Conversely, the 181 series with only a one-stage liquid transmission employed a one-stage 3-element converter to prevent a drop in tractive effort as speed increased, but there were limits. Around 65 km per hour, the two systems reversed, with the gas turbine vehicles gaining the advantage thereafter. Tractive effort alone did not showcase the lightweight benefits of gas turbine vehicles. Therefore, to illustrate this more clearly, the overall train acceleration was depicted in this chart. The starting acceleration of the gas turbine vehicles, in simpler terms, was about 1.5 km per hour per second, meaning the speedometer needle increased by 1.5 km per hour every second. Comparable to limited express EMUs designed for flat lines at the time, it was not a very favorable value for mountain line vehicles. On the other hand, around 90 km per hour, it was 0.9 km per hour per second, increasing speed by 9 km per hour in 10 seconds, making this acceleration quite impressive for the time. The vertical axis of this graph can be read directly as the value of the gradient, allowing one to determine the speed achievable on a gradient. To know the speed on a 25 per mile gradient, move horizontally from the 25 mark on the vertical axis until you intersect with the red curve indicating acceleration, then read the value on the horizontal axis at that point. In this example, it is 90 km per hour, which is better than the planned 80 km per hour. However, when there is a gradient on a curve, the curve resistance adds to the gradient resistance. For a curve with a radius of 300 meters, you need to shift the reading 2 to 3 marks upwards, resulting in about 85 km per hour. Let's compare this with the 181 series on this diagram. The gas turbine vehicle is over 20% lighter, giving it a significant advantage over the 181 series. Even though the 181 series has good initial tractive effort due to its transmission, the acceleration performance reverses around 45 km per hour. In the high-speed range, there is about a 1.5 times performance difference. Considering operations on regional lines without track improvements, many stations have turnout speeds limited to 35 km per hour to 45 km per hour, where acceleration from these speeds is impactful. While the transmission aids the initial effort, its effect is limited to station departures, and for limited express trains with few stops, it hardly reflects in travel time. At the time, this vehicle was considered for deployment on the Hakubi line. It was anticipated that after the Sanayo Shinkansen opened, the transport route from Kansai to Sanin would shift via Okayama, elevating the Hakubi line to mainline status. Let's calculate the extent of possible speed improvements. The track data on hand is from the 1970s, and some track improvements have been made since this plan, so the conditions differ slightly. However, we can roughly estimate the effects of introducing gas turbine vehicles. The curb passage speed is set at the standard speed plus 20 km per hour, with a maximum speed of 130 km per hour. When the 181 series limited express Oki was introduced to the Hakubi line, the curb passage speed was set at the standard speed plus 5 km per hour for high-performance express trains. The maximum speeds were 120 km per hour between Okayama and Kurashiki, 85 km per hour between Kurashiki and Hokidaisen, and 95 km per hour between Hokidaisen and Yanaga, which will be applied to the 181 series. For the Okayama-Yanaga section, the standard running time for the 181 series was 2 hours 21 minutes and 17 seconds, summarized as 2 hours and 31 minutes in timetable format. In contrast, the gas turbine vehicle's standard running time was 2 hours 2 minutes and 39 seconds, summarized as 2 hours and 13 minutes in timetable format. Now, let's consider the fuel consumption. For the 181 series on this same section, it was approximately 725 kilograms, while the gas turbine vehicle consumed 1,200 kilograms, about 1.7 times more fuel. Despite the lightweight body and reduced deceleration on curves, the fuel efficiency result is poor, given that the actual running time is about 15% shorter. One major reason for this is the significant fuel consumption of gas turbines in idle mode. To maintain idle status, a powerful compressor must be spun at over 10,000 rpm even when idling. As a result, 1,000 horsepower engines consume 50 to 60 kilograms of fuel per hour just idling, nearly 10 times that of a diesel engine. During the running time of this journey, the train consumed 214 kilograms of fuel while coasting or braking with the engine idling, which is quite serious. If this could be reduced by a third, the fuel consumption would be about 1.46 times that of the 181 series. Even though this was before the oil shock, JNR had long been addressing the idling issues of DMUs. Diesel vehicles, particularly those with poor startability, often idled the engine overnight in cold conditions, seeking methods of heat retention and preheating. While gas turbines did not have starting issues in cold weather, the significant fuel consumption during coasting was problematic, and serious consideration was given to engine cutoff mechanisms. Gas turbines could be restarted quickly and easily, so the frequency of starting and stopping the engine, and its impact on engine life, were also subjects of study. These engines were entirely new experiences, with no previous experience with steam or diesel engines to draw upon. There was some resistance to the introduction of gas turbines, partly due to the involvement of different industries. However, engineers were convinced that speed improvement was the only way for railways to survive. Despite JNR's severe financial situation, the potential of this initiative to deliver maximum speed improvements with minimal investment in track was highly anticipated, and it was a challenge tackled collectively by JNR and related industries. Later, when the replacement of the 181 series became necessary, there was a period when power-concentrated format diesel trains were considered. However, it was impossible to achieve performance levels that could be called high-speed trains, and the lack of formation flexibility meant the idea was never realized. Thus, power-concentrated format DMU trains never took root in Japan.